We're coming to the end of Chapter 9, which was air standard cycles. And the most recent air standard cycle we covered was the Brayton cycle, which is the model for the gas turbine engine. And the gas turbine engine is so widely utilized nowadays. I've sought out some photographs of how gas turbine engines are used in our everyday life. So I'd like to just give you an overview of the type of things where gas turbine engines are used and let you maybe think a little bit about career planning. Have you found the Brayton cycle model to be interesting? You think, yeah, I think I could catch on to something like that, um, or the type of equipment associated with the Brayton cycle gas turbine engine. So let's have a look. What I'd like to do is show you some images of stationary gas turbine engines, land-based, aircraft gas turbine engines, how they're used in different applications, and then finally, marine gas turbine engines. So remember, in all these examples that are coming up, basically we model these engines with the basic Brayton cycle. And, depending on your level of complexity, your level of need, you might be modeling as an ideal cycle where the compressor and turbine are reversible and adiabatic, and you'd be seeking to find the thermal efficiency of that ideal cycle. Or a little more sophistication, you might recognize that there is a turbine efficiency due to inefficiencies or irreversibilities in the turbine. Similarly, compressor inefficiency where there are irreversibilities within that process. Let's see, also remember that in the world, we combine fuel and air to provide the high temperature feed to the turbine. In our Brayton cycle model, what we're doing is modeling that combustion process as high temperature heat addition. The other thing to remember is you could basically bundle up this set of steady state, steady flow processes and jam them into this black box, the system operating in a cycle at a steady rate to visualize what's going on. Here's the rate at which you're adding heat, and here's what you're seeking to do, W.net. You're seeking to produce net power in some way or another. And so this is a classic image of a stationary gas turbine that's used to either drive a generator or drive some other piece of equipment that may be maybe a natural gas compressor or some rotating piece of equipment. And so you can see with your eyes, let's see, what have we got? We've got the inlet to the compressor coming in. We've got an open system, steady state, steady flow compressor. Look at these, a good number of stages associated with the compressor. And here's the outlet of the compressor. It does turn out that engineers have made entire careers working on the compressor section of gas turbine engines. They may not even have been working on the other components of the engine. Here's the combustion chamber section. But remember, in our world, we're modeling the combustion process as high temperature heat addition. So that gives us a very high temperature inlet to the turbine section. And so the turbine section, I see at least in this sketch, we've got 1, 2, 3 stages of turbine, and it's providing so much power that it's able to drive the compressor, the power needs of the compressor, plus it provides more than enough power so that we can continue this rotating shaft going out to the generator. And of course, then there's the outlet of the turbine. So a classic example of a stationary gas turbine. Here's another cutaway view of another type of stationary gas turbine, just to give you a way to have a look at the multiple stages of the compressor. We observe how the specific volume is decreasing. It's a compression process. Pressure is increasing, of course. Okay. It's just extraordinarily interesting to be able to see the different stages and the way they look in the physical world. Of course, here's our combustion chamber section, followed by the turbine section. Again, for me, it's just interesting to see, well, let's see, a turbine, that's an expansion process. So the pressure is decreasing and the specific volume is increasing. And that's the way we observe sort of that, the conical shape of the turbine with the exhaust gas going out, of course. Here's another view of a gas turbine engine, General Electric stationary gas turbine engine that is used to drive a generator. So this is going to be the outlet shaft that's driving an electric generator. Here you see in cross section the inlet, steady state, steady flow inlet to the compressor section, combustion chamber section, and then the hot exhaust gas. A little bit more on that, on how we might utilize that hot exhaust gas in the next video. Let's move on to aircraft engine applications. These are some pictures of a turbojet engine application. So and what have we got here? So you see there's two engines associated with this fighter jet. And how's that fighter jet being propelled through the air? Well, it's the kinetic energy of the outlet of the engine. So let's see what's going on with this engine that's not driving a generator. So turbojet, wow, so you see that there's plenty of moving parts, the compressor and the turbine sections within the engine. But do you see that if I were to draw a control surface around that whole engine, there's no moving parts outside of that control surface. So how is that jet being propelled through the air? Well, it's this high kinetic energy thrust that's being produced by the outlet velocity of the engine. And so for this, if you were to analyze, let's say in a class or as an engineer, do you see that for this situation, the output power of these three stages of the turbine would be used to drive this multi-stage compressor, okay? But then, so that's going to be a balance, isn't it? A balance of power, output power versus power required to drive the compressor. And that's going to give you something left over. And that something left over is going to go into a nozzle. So do you see that this could be considered a nozzle? And we'd be increasing the kinetic energy of the exhaust gas, and that's what gives us the thrust to propel this aircraft through the air. And here's just a great classic example of dual gas turbine engines with afterburners burning. So for example, on this image, there would be an additional supply of fuel back here to increase the exhaust gas air temperature even further to give you higher thrust, higher kinetic energy at the outlet of this nozzle. Another type of aircraft engine would be called the turbofan gas turbine engine. Well, let's see, as I move my picture around, okay, let's start at the bottom right. If you go to Goodwin Hall, it's going to smack you in the face if you look upwards to see the Rolls-Royce Trent 1000 engine that's suspended, and to some extent a cutaway view of that engine right there in Goodwin Hall. So I do recommend you make a visit so you can see with your eyes, where would the compressor section be? Where's the combustion chamber section? Where's the turbine section? Where's the inlet? Where's the outlet? So of course, in this image, we're looking right straight down the inlet of the turbofan engine. So let's see, what's this all? Well, let's go upwards. Here is the installation of the Trent 1000, and I believe it's on a Boeing 767 aircraft, of course, located underneath the wing. And here is an image of that Rolls-Royce Trent 1000 turbofan. So what's a little different about this? What's somewhat non-traditional? Well, notice here this initial stage. You see this sort of initial section here? Visually, I'm trying to show it with my cursor here. Do you see that that's not exactly part of the compressor section? So do you see that it's actually a fan? Okay, so the shaft is part of the turbine section. This aft part of the turbine section is driving this fan. So it's rotating the fan, and the fan is providing the outlet blast of the fan is providing kinetic energy to propel this Boeing 767 through the air. Well, that's going to be part of it, isn't it? So that's the fan section. But then also you have a turbine section that's driving the compressor, okay, in order to get you high pressure air into the combustion chamber. And so this is the traditional Brayton cycle model. So it's a turbofan. So you see, it's a combination of engineering components that's providing thrust, and of course, ultimately, the idea is to provide thrust to the aircraft. And so it's the combination of this fan plus the kinetic energy of the outlet of the gas turbine engine. Now, a lot of folks that have interest in aircraft, you say, well, I remember the Wright brothers. I remember the two world wars. Um, and I remember that aircraft during those times used internal combustion piston engines. And those piston engines were used to drive a propeller. And so propeller technology really did evolve, of course, long before the Brayton cycle became viable. So here's some examples of what we call turboprop engines for aircraft. For me, I was thinking, where can I grab some images? Of course, early on. So here would be some of the earliest stages of gas turbine engines driving propellers here for a private aircraft. So we've got two gas turbine engines driving two propellers. Here's kind of a cutaway view of a gas turbine engine driving a propeller that's, of course, removed from the aircraft. An example of the C-130, which has multiple gas turbine engines driving multiple propellers. And you say, well, what's the difference? Why aren't all aircraft turbojets? Well, I think now this is out of my field of expertise, but I believe it has to do with the speed of the aircraft. And so the speed of the aircraft, the size of the aircraft, the drag loads on the aircraft, all of those things go into the engineer's decision on what type of gas turbine engine will we select, a turbojet, a turbofan, or a turboprop. And this, I've been fortunate to see an Osprey operate up close and personal. And so this is, I would say, one of the newer vintage inventions where the rotating gas turbine engine is driving a huge propeller that almost looks like helicopter blades, okay, but able to amazingly during operation rotate and propel this aircraft horizontally through the air, but also propel the aircraft upwards and lift the aircraft up in a vertical takeoff position. So an amazing piece of technology, an amazing invention using the turboprop design. I discovered this example, this USS Freedom high-speed warship, as a result of being at a presentation by a Virginia Tech graduate who got into the Navy and became an officer in the Navy. And he rose to the level of admiral in the Navy. And he made an inspiring presentation and talked about some of his engineering work in his responsibilities in the Navy. And this is a screenshot of this USS Freedom class warship. And I looked up after his presentation on Wikipedia to see that the speed of this ship is rated at 54 miles an hour. That blew my mind. I said, this can't be a ship going through the ocean at 54 miles per hour. And so to learn more, I said, well, how is this being propelled through the ocean? Well, it's taking two Rolls-Royce, it says MT-30, whatever that is, 36 megawatt gas turbine engines driving almost like a jet ski. And so you can see here that each of these engines is rated at 48,000 horsepower. I found this to be extraordinarily interesting. Of course, here's the warship being propelled through the water at speed, at rated speed. And here's what one of those gas turbine engines looks like. It's sort of amazing. And with your now a growing expertise, you could identify in this image what's what. Well, that you can see that this would be the inlet of the compressor section. You can see where that would be the combustion chamber section, followed by the turbine section. And this turbine is producing enough rotating power. And so here in our overall view, we've got an air inlet going in here, okay, with the combustion chamber section, turbine section, and then exhaust gas coming out. But there's plenty of power produced in this turbine section to have this shaft rotating. And amazingly to me, this rotating shaft that's producing 48,000 net horsepower, it's not going to a propeller. It's going basically to a water pump. And that's the way a jet ski works. That the rotating power goes essentially to a pump that takes in water from underneath the vessel and increases that pressure, increasing the kinetic energy of the water. And that's what provides the thrust for the vessel to go through the water. And so I tried to think how that is so much power to me. So what's an analogy there? It's sort of like a jet ski times 1,000. And so a jet ski on let's say on average could be rated around 48 horsepower. Of course, a jet ski, of course, operates with an internal combustion engine, but you see the analogy. So this sort of blew my mind, that this application for a gas turbine engine in a marine application. So what's our takeaway here? And I hope that some of these slides, images might maybe pique your interest in saying, I could see working on something like this as a job, as an engineering career, or even a starting career. So recognize that the basic Brayton cycle is widely implemented. High net output power is possible. Of course, it takes a lot of energy to produce that high net output power. And also recognize that there are thousands of engineering and leadership opportunities associated with the gas turbine engine. So that's what I wanted to share with you, give you some look at what do some of these photographs look like, what are the practical applications, and how might it interest you as you're thinking about what you might want to do either as you're seeking employment after your undergraduate experience or after your graduate school experience.